Welcome to Introduction to Composites. Today is the third day of the ongoing week, which is the 11th week of this course. Yesterday and the day before that, we had developed relationships between strain and displacement functions and also stress and strain for composite laminates. Today, in the beginning portion of this class, we will explore these two issues a little bit further, and we will try to understand how do these stresses and strains vary along the z direction, that is, for a given value of x and y. If we move in the z direction from top surface of the laminate to the bottom surface, how do these stresses and strains vary? So, consider a laminate, and we will consider a simple laminate which has, let us say, just 3 layers. So, this could be layer 1, this could be layer 2. So, this is 1, this is 2 and this is 3, and the mid plane of the system is somewhere here. Okay. So, this is I am going to draw this again, and one thing we have developed for strain is the relations which we have developed for strains are something like this, that epsilon x, epsilon y, gamma x y equals epsilon x naught y naught gamma x y naught plus z times curvatures. Okay. So, along this line AD, this is my line AD, this is again AD, the value of x and the value of y do not change. The only thing along line AD is changing is the coordinate z, x, y are not changing, which means this function does not change. There is no change in this function because x is fixed and y is fixed. So, mid plane strains are fixed. Similarly, the curvatures are also not changing, mid plane curvatures are also not changing along line AD, because what is curvature of the mid plane? It is second derivative of w with respect to x, y or x and y. So, this is also not changing. The only thing which changes is the z coordinate, the only thing which changes is the z coordinate. So, and at the mid plane the value of z is 0, at mid plane the value of z is 0. So, at mid plane what will be the strain? It will be the mid plane strain. So, suppose we want to plot along line AD epsilon x. So, strain will be mid plane strain, and then as I go up or down, depending on whether curvature is positive or negative, this strain, overall strain will vary linearly, because it is a constant plus z times another constant. So, it will be just a straight line. Okay. So, the overall line may be something like this, where this represents the mid plane strain, this represents the mid plane strain, okay. And the slope of this line represents the curvature, and it just is a straight line. So, this is how strain varies along the thickness. Now, it can have a positive slope, it can have a negative slope, it all depends on the value of curvature. Okay. But the point is that along line AD, strain varies linearly across the entire thickness of the plate. So, this is something important to understand. The second thing we have to understand is how does Q vary Q. So this is again AD, and these are the 3 layers. Okay. And here what we are going to see is how does Q matrix vary, and we will just consider one single element Q11 bar or something. Okay. So the orientation in layer 1 can be some theta, and then in layer 2 it can be some other theta. So the change in angle is not sudden, is not gradual, it is sudden. Okay. So if it is sudden, it means the Q bar matrix for the first layer will be something, and for the entire matrix, for the entire first layer it will be constant because it is same material and same angle. But for the second layer, if theta changes, then suddenly Q bar will change, and then for the third layer it will again suddenly change. So the Q bar matrix, it changes suddenly. So it can have any, so for a given layer it is constant, because for a given layer theta is constant, material is same. So for a given layer it is constant, and as you move from one layer to other, the Q bar matrix jumps. So this is how Q bar changes. And finally, we look at how does stress change. Now we know we had developed this relation between stress and strain for the kth layer, right. So stress is equal to Q bar matrix times epsilon naught plus Z times Q bar matrix times curvature. Okay. So what does that mean? Strain is varying linearly, Q bar is jumping, and it is discontinuous. So what that means is within a layer strain will vary linearly because Q bar is constant. Within a layer Q bar is constant, so this is constant, epsilon is constant, K naught is constant. So the only thing within a layer is varying is Z. Okay. So within a layer stress changes linearly, but as you move from one layer to other layer, Q bar changes abruptly because we have shown it here, and as a consequence stress jumps from one value to other value as you move from one layer to other layer. So the stress distribution or the stress function along the thickness of the plate, so suppose these are 3 layers, so the stress could vary something like this within a layer. Then because Q bar is changing and Q bar is becoming very small, so it becomes very small, and then again it changes linearly over the second layer, and then again Q bar becomes large and again it changes linearly. So within a layer, so stress inside layer it is linear, and across layers it is discontinuous. Okay. Across layers it is discontinuous, within a layer it is changing linearly. Strain, it changes linearly over entire thickness. Okay. And Q bar matrix, it is discontinuous. What about Q bar matrix? It is inside layer constant, and across layers discontinuous. So, in this case, right. So, this could be something like this. Okay. So, these are the three important observations. Strain varies linearly along the entire thickness of the composite. The Q bar matrix and elastic properties are constant within a layer, but across layers they jump and they are discontinuous, and stress is discontinuous across layers, but within a layer it varies linearly. So, this is something important to understand, and with this we move to the next part of our discussion, and we will introduce a new topic which is related to this and very useful, and these are resultant forces and moments. So, we define resultant forces as N's and moments as M's, and these are resultant forces and moments per unit length. They are not, their units are not newtons and Newton meter, because they are per unit length. Okay. So, we will actually define that. So, first we will explain the concept. So, suppose you have a composite sample, this is my mid plane, okay. This is my z axis, this is, let us say this is x, this is y. Okay. So, the stress in the x direction on this face is sigma xx, it is sigma xx. If I integrate this sigma xx in the z direction, so I integrate in the z direction and I integrate it from, so let us say the total thickness of this composite laminate is h millimeters or h meters. So, I integrate it from plus h by 2 or minus h by 2 to plus h by 2. Okay. So, my integration limits are minus h over 2 to h over 2, where h is the thickness, then this is called Nx, this is called Nx, and essentially it is the force. So, if I integrate sigma x over this entire area, just think about it, if I integrate this sigma x over this entire area, then what is it? It is the total force which is being exerted in the x direction, and if I divide that total force by this distance a, then it is force per unit length, right. So, Nx is basically force which is being applied in the x direction on the composite laminate in the x direction per unit length, and that is sigma xx times dz, integral of that. Okay. So, similarly we define other quantities. So, Nx is equal to integral of minus h over 2 to h over 2 sigma x dz. Similarly, Ny. So, what is Ny? In this direction, this is sigma y. So, if I integrate sigma y on this entire surface and then I use it on a per unit length basis, then I get Ny. So, that is equal to sigma y dz. And the last force resultant is called Nxy, and it is basically the integral of shear. So, this is sigma xy, this is sigma xy. If I integrate it on, if I integrate sigma xy on this entire surface, or I integrate sigma xy on this entire surface, then I get the force resultant nxy. So, nxy is equal to minus h over 2 to h over 2 tau xy dz. So, and their units are newtons per meter or newtons per or newtons per meter, or sometimes we also use as MPa millimeter, it depends. Okay. If we want to use thickness only in millimeters, then it becomes MPa millimeters, otherwise to be internally consistent, newtons per meter is mathematically more consistent. Okay. So, these are force resultants. So, these are not forces, these are force resultants, force resultants. Similarly, we have moment resultants. Okay. So, we will again draw pictures to make things clearer, and then, so suppose I have a composite plate. This is my mid plane, okay. And if I am having stresses in the x direction, let us say this is sigma x. So, what will that stress do? It will try to bend the plate up or down. So, it will not only try to pull it, but if it is off center, then it will also try to bend it up and down. Suppose the stress is more on the lower half and less on the upper half, then the plate will try to bend upwards. If stress is more on the upper half and less on the lower half, then plate will try to bend down. So, plate will not only stretch because of stress, it will also try to bend. So, how do we figure out how much, and that bending will depend on the moment it will generate. Okay. So, we call this moment mx. So, suppose this is my x axis. So, if it tries to bend upwards, we call it positive mx. This is positive mx. Okay. And x, what does it represent? X represents the normal on the plane which it is acting. Similarly, on the other surface, so this is my y axis, and there is a my, okay, and that my is a consequence of sigma y. If sigma y is uniformly spread above and below the surface, then my will be 0. If it is not uniformly, then my will be non-zero. And then there is a twisting component. So, twisting component will be look something like this. So, this is mxy, okay. And similarly here it is like this mxy. And how do we calculate the values of these m's and mx, my, mxy? So, again these are not moments, these are moments per unit length, moments per unit length. So, what is moment per unit length? It is basically integral. So, we will write one relation, mx is equal to integral of minus h by 2 to h by 2. So, if sigma x we integrate, and we integrate not sigma x, but also sigma x times the distance times z dz, then it is mx, which is moment per unit length in the x direction. Okay. moment per unit length in the x direction. Suppose I multiplied this by entire area A, then it will be the actual moment, this entire length A, then it will be. Similarly, my is integral of minus h by 2 to h by 2 sigma y z times dz, and mxy is integral of minus h by 2 to h by 2 tau xy z times dz. So, essentially what we are calculating right now are forces acting on a plate per unit length on each edge and moments acting per unit length on each edge. Forces per unit length are defined by n's, which are integrals of sigma x times dz, sigma y times dz and tau xy times dz, and moments per unit length are sigma x times z times dz integral, my is sigma y z dz and mxy is tau xy z dz. Okay. So, these are moment resultants. Moment resultants, and what are their units? So, this will be MPa is the stress and times dz times z. So, then you can have millimeter square. This is one, or if you are not integrating it in millimeters, if you just use meters, then it will be basically newtons. So, I like the Newton unit better because it is mathematically more consistent, but lot of times people also use these mixed terms MPa times millimeter square. So, you should be aware of that. Okay. So, next what we will do is we will actually calculate mx, my, mxy, nx, ny, nxy in terms of, so we already know how these stresses sigma x, sigma y, tau xy are related to strains. So, we will put these equations for stress strain displacement strain stress relations in these relations for moment and force resultants, and then based on that we will develop a model for the behavior of a composite plate when it is subjected to externally known moment and force resultants. So, that is what we plan to do in our next class, and till then I think it will be very important that you review all the material which we have covered, particularly in this week, because that will be very useful and important for you to know when we move on to this adjacent topic tomorrow. Thank you and have a great night. Bye.